Hello everyone, today we will be discussing the lecture number 33 of the NPTEL lecture series on charging infrastructure. And in this lecture, since we have been revisiting our isolated DC converter, now one important thing which we must understand is about the switching losses and how that losses occurs, that we will discuss in this lecture, because that will actually form the base for the next stages of discussion of isolated DC-DC converter, specifically the full bridge converter, the PWM strategies, and their another kind of modulation which is phase shift based modulation. So that's why in today's lecture we will discuss about the switching losses and on what factor the switching losses depends, and because this will help us to understand the concepts for future lectures. So that's let us discuss that. Now before starting that, let us recap what we have discussed as of now. We have discussed some of the isolated DC-DC converters, and in all most of these isolated DC-DC converter, what we have DC which is actually getting converted to high frequency voltages, and that will be actually applied across on the secondary winding, and accordingly we will then do the rectification and then we will get the output DC. So in this thing we have revisiting some of the converters, like we have visited forward converter, again different configuration of forward converter. We studied forward converter with demagnetizing winding, dual switch forward converter. Then we have seen push pull converter, and after that we have in the last lecture we have discussed on the full bridge converter and half bridge converter also we have seen. Now mostly for high power applications, generally people prefer full bridge converter operation, primarily because the core is fully utilized, and also the voltage ratings of these devices are actually just the input voltage, and also with this kind of converters we can also achieve the reduced loss operations as well. We will discuss that in subsequent slides. So we will discuss more in detail on this full bridge converter as we go along in subsequent lectures. So before starting that, we have seen that we are converting the DC into the high frequency AC, and that will be applied across the one of the transformer winding, and accordingly voltage gets induced on the secondary windings, and then it will get rectified and applied to the load. Now in this one we have seen that the why we went for configuration something like this, where the transformer sees the high frequency excitation. It's because with increase in frequency the requirement of the cross sectional area of the core is less, and that's when we can reduce the size and weight of the our entire power converter. So that is one of the important factor. So we are actually going from the DC to high frequency AC, and that AC is applied across the transformer winding. And since we would like to have smaller and lighter power converter, because that's one of the requirement, since these converters are most of the times are either put on the charger or on the vehicle in the form of onboard charger. So we must ensure that the converter should be lightweight and smaller in size, and one way to achieve that is to go for high switching frequency. And also since we are going for a high switching frequency, we have corresponding switching losses in the switches, and that we will evaluate, of that we will see how those switching losses depend in this particular lecture. So we have seen some of the operation of full bridge converter in the last lecture. Now let us start our discussion related to the switching loss, because we have seen that if we increase our switching frequency FSW, if we are increasing, our cross section area requirement of the core gets reduced. Also the inductor and capacitor sizes are actually inversely proportional to switching frequency, and that is when we can also get smaller inductor and capacitance. I mean inductor and capacitor, I am talking about filter capacitor and inductor. These are all filter components, I mean which was placed at the output of this converter. It is purely because we know that our cross section area is nothing but V number of turns N delta B and FSW. So for the constant voltage number of turns and the maximum delta B, our AC or the cross sectional area of the core is inversely proportional to the switching frequency. And the other thing, we have, if you recall our inductance value, what we have got, N V in D 1 minus D divided by 2 FSW and delta IL. If you recall our last class discussion, we got this inductance value. Similarly, our capacitance value, obviously we are writing here for full bridge converter. So this capacitance value, what we got was, we got our capacitance value to be delta IL 8 2 FSW delta V naught. We got this particular capacitance value, this. So this is the inductance value and capacitance value, obviously this is for full bridge converter. And in both the things we see that the inductance and capacitance value is inversely proportional to f switching frequency. That means if I increase the f switching frequency, my size of inductor and capacitor is less. Further, if you look any DC-DC converter, I mean whether it could be our buck converter, buck boost converter, or our boost converter, or isolated converters, in all the converters what we have some set of switches, maybe 2 or maybe 4 depending upon the kind of converter we have. Then we have filter inductance, filter capacitance, and if it is isolated DC-DC converter, we have the isolation transformer. And in all the things, if we look very carefully, the switches, the size of the switches and auxiliary circuit for those switches are not too much as compared to the size of our L inductance, capacitance, and high frequency transformer. So the size of power converter is directly proportional to the size of, we can write size of power converter is directly proportional to size of L, C and high frequency transformer. And these all this L, C and high frequency, you can say that these are passives, you can say these are passives because they do not have any active component involved in that. So the size of power converter is directly proportional to the size of passives, and the size of passives is inversely proportional to the f switching frequency. So if we increase our f switching frequency, size of passives goes down, size of passives goes down, and if our size of passive goes down, our size of power converter, size and weight, I mean both size and size, we are talking in terms of volume as well as weight, size and weight of power converter also goes down. That means our prime objective is to go for higher switching frequency. That is when we can reduce the size of passives, and that is when we can reduce the size of power converter. However, when we go for high switching frequency, we have the switching losses which will be occurring in the switches. Now let us try to understand what will be the switching losses, I mean how we can evaluate switching losses and in what factor the switching losses depends. So let us take, for calculating switching loss, let us take a simple buck converter. So if we take a simple buck converter, what we have is, we have switches and the diode. So this is a S1 switch and this is a diode D, and let us take the output to be an inductor and a capacitor and a resistance RL. Okay, this is V in, this is V naught we have. Now if we look very carefully, this particular bridge, the connection of the, I mean the switch and the diode, you can also get the same thing by just having another switch instead of diode. We could have the synchronous rectification where we remove this diode and connect another switch, and whenever my S1 switch is off, I will turn on my S2 switch, and vice versa, and whenever my S2 switch is on, I will turn off my S1 switch. Both will have the same kind of operation. So to understand our, to have the basic understanding, if we see, we could have also achieved this thing by my S1 switch, my S2 switch with a freewheeling diode, or you can say a body diode if I am using a MOSFET, and this capacitance, and then we have the resistance RL and output V naught, input V naught. And both the things what we will see is, we have this particular converter, this particular half bridge, which is one of the a conventional, or you can say one of the building block of any voltage source converter. So we can then, and since we have this LC and this LC at the output of this switch and diode connection, so here what we will see is that if you see the IL current, what we have is IL current will consist of nothing but average value, which is nothing but going to I naught, current going to the load I naught, and it will have some ripple to it, and let us assume this ripple delta IL to be very small. If we assume this inductance value is very large, then we can say that the output of this combination of S1 and D is nothing but it is the a constant current coming out of this, or you can say the constant current, I mean current with a small, this variation or and a small ripple. So we can then take a circuit which is nothing but a circuit looks like something like a constant current coming out of this, and this is nothing but D, this is S1, this is V in, and this is I naught current going on. I mean, on that I naught current we have a small ripple, but we can assume that this ripple to be very small, so we can assume this circuit. Now let us see how our losses in the switch S1 looks like. So let us try to understand the scenario where what we have is we have circuit. This is V in voltage which has been applied, and if we see that, so in this particular circuit if we see, let us try to draw V, I mean the voltage Vs1, and let us assume the current which is going through the Vs1 is Is1. The current which is going through the switch is nothing but Is1, and the we can say that the whenever my S1 is on, the Is1 is nothing but equal to I naught, and whenever my switch is off, the I naught will be circulating freewheeling from this diode D. So let us try to make our understanding, because if you look very carefully, this is most of the time we can have the bottom synchronous rectification, that means switch along with this freewheeling diode. So it is like a conventional, you can say, the half bridge. So let us try to see, find out the losses in the switch S1. Let us make the switch goes from here it was off, it goes to, let us say, on, and then maybe after some time it's get on here, and that it is off here. This is gate pulse of S1. Now since we have gate pulse of S1 look like this, so at that point, since my switch turns on, what happens is that the current through the switch will start rising. If I write IS1, so it will start rising. I am just trying to zoom out the instant. So this start rises and it reaches to I naught value, and till the point my Is1 is not equal to I naught, the remaining portion, because see, if you look very carefully in this circuit, there is current which is coming through the Is1, and I mean the other possible way, there could be some current going through ID, through the diode. So I naught is nothing but equal to Is1 plus ID in this particular kind of half bridge if we take. So in this thing what we see is that the I naught is nothing but Is1 plus ID, and if you look very carefully in this thing, since my Is1 is not equal to I naught, there will be some diode current which is going through it, and that is when the voltage across this diode is nearly 0, and that is when, since the voltage across the diode is nearly 0, the voltage across the switch S1 is still holding this V in voltage, because previous to that it was having the voltage V in, if we Vs1, since it was off, it was on, so the entire voltage will be appearing across this S1 switch. So we were having the voltage V in, and then the moment at this time you have given the signal to turn on this S1 switch, the current slowly start rising through the S1 switch, and then some portion is coming from this channel while this other portion of the output current is coming from the diode, and because it is coming from the diode is forward biased, and since it is forward biased, so this voltage is still, this point voltage is still hold to 0 volt. If we take with respect to n, it is still hold to 0 volt, and that's when the entire DC link or entire V in is actually coming across the switch S1. So the switch will still be having voltage S1, and then after some time, whenever the current reaches to I naught value, at that point the diode gets reversed bias, and that's when the voltage which was here will now then fall to 0, because if it is get reversed bias, this voltage will start appearing across the diode. So what we see is that the voltage will fall down and becomes 0. Now here we assume some considerations that switches when it is off, it is I mean it is having 0 voltage, and when it was not conducting, the current through the switch is actually 0. So that is the some consideration, and we have also not considered any forward voltage of the diode and the effect of nonlinear input and output capacitance of devices for our easy calculations. So now there is a time when their current is rising. So let us say this time to be TRI, the rising of the current, and there is a time during which my voltage is falling. Let us say this time to be falling of the voltage TVF, and then we can say the T switch on, the time for turning on the switch is nothing but equal to TRI plus TFV. And if we see this particular system, if we try to find out the losses which is happening through the switches, so let us first try to, let's try to find when T is between 0 to TRI, that means from this point to this point. If we assume this to be T equal to 0, then we can say that IS1, which is also varying with time t, if it is all these are with varying with time t. So this is a rising thing, so we can write this is to be nothing but I naught divided by TRI into T. Similarly, we can write Vs1 of T, the voltage across this one is to be nothing but equal to V in voltage, and that's when we can now evaluate our energy loss during TRI period, energy loss during TRI period, that means during the rise time of current, where Ts is nothing but 1 by FSW. So what you can say, if it is off over here, and let us take some time that after off, after some time it gets on here again. So from here to here we have Ts period, and we can also say that during when it is turned off, when the switch gets turned off, what happens is that we have the first the voltage which gets rises up. When it is turning off, it is the vice versa which will happen, where the voltage will first rise to V in voltage, and when it rises to come to V in voltage, then only the diode will get forward bias. Otherwise, if it is not V in, then there is some positive voltage which will be appearing across cathode to anode, or you can say the cathode will be at higher voltage as compared to anode, and that's when it was reverse bias. So during this time it reaches to V in, and then only your current, till that point your current will be with the IS1, and then after that only it will goes down to 0, and that is when here the current will be flowing through the ID1 at this place. So through the diode, so that is why we can say this point we have 0. So in the switching cycle, if we see turn on is happening once in a switching cycle, that's why we are taking the average energy loss during the TS duration in the TRI region. So let us try to find out the energy loss during TRI period. So it is ETRI, we can write nothing but equal to IS1 and Vs1 of t, and that will be nothing but dt going from 0 to TRI period. So that means we can now take energy loss during TRI period to be equal to ETRI to be equal to 0 to TRI I naught TRI T Vs V in and dt. So that will be V in I naught, and TRI comes out. This will be T dt 0 to TRI. Now that will be ETRI to be equal to, or the energy loss during TRI period, we can write V in I naught by TRI to TRI square by 2, and that we can write V in I naught by 2 into TRI. Now that, let us define this as equation number 1. So what we have done, we have calculated the energy loss, only the energy loss during the TRI period, and then let us calculate the energy loss during TFE period. Now let us take when the time is going between 0 to TFE period, that means during this period of time, from here to here. Now if we look there, so we can write IS1 of t is nothing but equal to I naught, but my Vs1 is actually going from Vs1 of t is nothing but equal to V in minus V in t by TFV. So that is what we will get the voltage across the device from 0 to TFE period. So then we can then calculate energy loss during TFE period. Now if when we do the calculation, we will get E TFV to be nothing but Vs1 t Is1 of t, and that is integrated from 0 to TFV. So this we can just put Vs1, we can just put V in minus V in by TFV into T into I naught dt 0 to, and then we can write down this thing to be nothing but, we can just take out V in I naught outside, and that will be 0 to TFV 1 minus T by TFV to dt, and this term we can write down as V9 I naught 0 to TFV T dt minus 0 to TFV T dt by TFV. That is, and this whole thing will come in the bracket. V in I naught, this one will be nothing but, sorry, here it is nothing but 1. So this will be T going to 0 to TFV minus here T dt, which is T square by 2, and TFV is outside. This is nothing but 0 to TFV. And this, when we do that, V in I naught will be nothing but TFV minus, we have TFB by 2, that is nothing but we will get finally ETFE, that means energy loss during this period, TFE period, is nothing but V in I naught TFV by 2. Let us define this as equation number 2. Now we know that what is the energy loss during this TRI period and what is the energy loss during this TFE period. So then we can now calculate the energy loss during the T switch on period, because this total is nothing but T switch on. If we see from the previous slide, is nothing but T switch on. So this period is nothing but T switch on. So let us take the energy loss during T switch on period. So the energy loss during T switch on period, so we can write it to be E on, you can say, is nothing but ETRI plus ETFV, which is nothing but, if we do V in I naught by 2 comes out, and TRI plus TFV from equation 1 and 2, and this is energy during turn on, we have V in I naught by 2 T switch on. That means the time during which the switches, the transition of voltage and current looks like. Now, since we have calculated our E switch on, and if we look very carefully, in one sampling period or in one switching period, TS period, our switch turns on and then it turns on in the next switching period only. So we can say that the power loss during switching on is nothing but, you can say that P switch on is nothing but V in I naught by 2 T switch on by Ts, which is nothing but, we can write P switch on is nothing but V in I naught by 2 T switch on times F switching. Now this is, let us define this as equation number 3, because this is the power loss during switch on, and we can also then see what is the power loss during switch off. So when it is switch off, we have understood that it was first I naught was remaining till this point and voltage is rising. So here we can just write this to be TRV, and this voltage, this time period to be T, since current is falling, TFI. And if we do this entire thing is nothing but T switch off. So during switching off or during turning off, you can say, when the device is going to turn off, so that time, when T is less than between 0 to TV, what we have is I switch 1 is to be nothing but equal to I naught, and Vs1 to be equal to V in T by TRV. Now that if we try to calculate energy loss during TRV, we will get ETRV is nothing but IS1 T Vs1 of T dt going from 0 to TRV. Now this we can then put the values and we will get 0 to TRV, V in I naught T by TRV dt, and we will get the same thing, V in I naught by TRV, it is T dt, so it is T square by 2, 0 to TRV, and finally we will get ETRV to be equal to V in I naught TRV by 2. So let us take the switching energy loss during TFI. So when T is between TFI and 0, we can write IS1 of T to be equal to, it is falling from I naught, so it is I naught minus I naught T by TFI, and Vs1 is nothing but Vs1 goes to V in. So that's when energy loss during TFI period is nothing but, we can write ETFI to be equal to 0 to TFI IS1 of T Vs1 of T dt, which is I naught minus I naught T by TFI V in dt going from 0 to TFI. And that when we do this thing, V in I naught comes out, it is T dt 0 to TFI minus 1 by TFI comes out, 0 to TFI. Now here it is, since here it is 1, here it is 1, this T dt, and this when we do this, we will get V in I naught T 0 to TFI minus 1 by TFI T square by 2, 0 to TFI. This when we do this one be in I naught to be TFI minus TFI square by 2, TFI get cancelled, TFI by 2, and that will be V in I naught TFI by 2. So this is nothing but ETFI, energy loss during the time when the current is falling during turn off. So it is nothing but, let's say, equation number 2. So we can say energy loss during turn off case is nothing but E switch off is nothing but V in I naught by 2 TRV plus TFI. Now we know that TRV plus TFI is nothing but T switch off, so it is nothing but T switch off. And then we can say the power loss during turn off or turn off power losses, we can say that, and this power loss is happening once in a switching period because it turns off only once in a switching period. So we can just say V in I naught by 2 T switch off into FSW, just like we got it in the case of during the turn on case. That we will define as a equation number 5. Now this one, this value we will get it from equation 3 and 4. Now we calculated the power loss during turn off case. Similarly, we have calculated the power loss during switching on or turn on case. So let us try to see the overall switching losses in the power converter. So we can say the power loss during switching, that means during turn on and turn off, is P switching or switching power loss is nothing but equal to P switch on plus P switch off, and that you will get P switch is nothing but V in I naught by 2 T switch on period and T switch off period. That means the time during which while going for turn on the current rises from 0 to I naught and voltage falls from V in to V naught, that time plus the time during which during turn off case the voltage goes from 0 to V in and then the current falls from I naught to 0, that summation of that particular time multiplied by FSW. And if you look very carefully, if we try to see how the loss varies, so from, if you take in this period this multiplication of this, we are seeing that it is going up, it reaches to a maximum value, and then here it is right, it is falling, it is this one, it goes down and becomes 0. So this is nothing but your you can say P switch in P or the power loss. Similarly, in this time here it is rising and this is constant, this is rising and this is falling over this entire period. So this is the nothing but the power loss during turn on switching on case or turn on case, and power loss during turn off case, switching off case. Now this particular term, if you look very carefully, the switching loss across the devices, because we have considered our converter to be, we have this S1 switch and the diode, and we have a current, output current from this kind of a bridge, half bridge, where we assume that the bottom switch is not in picture. We have only freewheeling diode or body diode of the MOSFET, which is being connected at the second switch or S2 switch in place of S2 switch. We have just considered the diode D. So during this period we have understood that the switching loss which is happening across the device S1, obviously we have calculated for S1 the switching loss for S1. Similarly, we can do it for if we have, let's say, two devices S1 and S2. So similarly we can do it for S2 as well. So however, what we understood that the switching loss depends on first switching frequency. That means if you keep your switching frequency higher, your switching losses will be higher, because P loss is directly proportional to FSW. And we can see also one more thing, that since in case of isolated DCC converter, we are going for high switching frequency to reduce the size of the passives, that means transformer and inductor and capacitor. We are actually incurring more and more losses, because we are having so many switchings, so many times the switches get switch on and off, and that is when we have so many occurrence of those loss of energies, and that is when we have higher switching loss. So depends on switching frequency, it depends on the blocking voltage, that means when it is off, the amount of voltage it is blocking, and when it is, when it is turning on, amount of voltage has to fall down, and when it is turning off, the amount of voltage which is needed to must be built across it. So that depends upon that blocking voltage. Then it depends on the current during switching instant. So you can say switching current, or the current which it has to go to when it turns on, and the current when it is turned off, the amount of current it has to go from non-zero value to zero value, that is the current. So that means the current during the switching instance. Here it was, we have assumed that this current is constant I naught, so here it is I naught. If it is having a ripple, then accordingly that ripple component also has to be added into the current, because when it is turning on, so that time my current through the inductor will actually be rising up, because we are applying the positive voltage across the inductor, and whenever it is turning off, we are applying the minus V naught across the inductor, that is when we have falling current. So during turn on instance, we have to take the current from I naught minus delta IL by 2, and while it is turning off, it has to be I naught plus delta IL by 2 current. So that ripple has to be considered when you are taking the exact calculation. However, roughly if the ripple is very less as compared to the average value, we can neglect that. And finally we have the turning on and turning off period, turning on, turning off time, or you can say period. That means the turning on and turning off, time corresponds to turning on, and we can write time required for turning on and turning off. So it depends upon that as well. So if we wanted to reduce the switching loss, if let's say if you are going for high switching frequency, so you cannot reduce the switching frequency. The other things which you can reduce is our the voltage blocking across the switch, or the current which is be carrying during the switching state. For example, let's say when the switch is going turning on, from off to on, if I can somehow ensure before turning on instant, if I can somehow ensure the voltage across devices goes down to 0, I can get the 0 switching loss. And while turning off, if I can somehow ensure before the current goes from non-zero value to 0, if I can somehow ensure the current goes to 0, I can ensure the switching loss is very less, or you can say 0. So this is what we will discuss in the next lecture. So in this lecture we have understood the factors on which the switching losses in the switches depends, and the same thing we can apply. Let's say if your system has, let's say 6 switches or 4 switches, you have to calculate the switching loss across each switches, and in the same manner how we have derived, we will get the same formula, and we can use the same formula to derive the switching losses, and that is when we can calculate the overall switching losses in a power converter. We will discuss more about this thing. I mean, how we what is the understanding we got from this thing, and how we can apply it to short switching scenarios. We will see this thing in the next class. Thank you for patiently listening to this lecture.